Welcome back, ladies and gentlemen. So we're going to be continuing with some kinematics. I'm going to work through a couple questions just to help people out who might be getting a little stuck. Today we're going to be taking a look at page 3 of your kinematics book, and we're going to be taking a look at question number 6. Question number 6 is usually the one where people sort of have a bit of a hard time. So this is going to be page 3, number 6. Now, let's take a look at what we got here. While driving a car, Miss Jensen sees an obstruction in the road. There's something in the way. It takes her 0.8 seconds to react and put her foot on the brake. Her car is traveling at 25 meters per second. Okay, so there's our starting piece of information. So we've got a car. Okay, and the car is moving along at 25 meters per second. We'll say that's positive. That'll be initial velocity. And then it also tells us a time of 0.8 seconds because somewhere in the distance there's some kind of barrier, and she apparently doesn't want to hit it. Who knew? People don't like getting in car accidents. Now, there's an A and a B to this question, and this is one of the reasons why it tends to throw people off. 1. How far will the car travel before she puts her foot on the brake? How far? We talked about this in the first unit. How far means I'm asking for D. Okay, so I'm saying in question A here, A, what is the displacement of the car? All right. Well, that seems simple enough. There's a trick. There's always a trick. With all of these questions, we're going to want to find the same 5 variables. So let's start writing out our variables. We've already drawn our picture. Pictures are very helpful. You're going to want to do that. Our variables are VI, VF, A, D, and of course, T. Now, we're going to collect our information and we're going to put it in. Well, we know that the initial velocity of the car was 25 meters per second. The final velocity of the car, there's so many possibilities here, right? I mean, first of all, it says, how far will the car travel before she puts her foot on the brake? Does the car start slowing down before I touch the brake? No, not really. So how fast am I going? Well, we'll get back to that. We're looking for how far. So that one's easy. I'll put a question mark there. We have a time as well. It says it takes 0.8 seconds to put her foot on the brake. So what is the acceleration and what is the final velocity? Because the rule is that we need 3 terms to find the missing 2. And right now we only have 2 terms. So we can't solve this as is. So what do we do? Well, we have to think through the logic. When I take my foot off the gas and I go to put it on the brake, until I touch the brake, the car doesn't start slowing down yet. I mean, okay, technically it does, but it doesn't really. Not until I hit that brake. So the final velocity during those 0.8 seconds is going to be 25 meters per second, give or take, because the acceleration is going to be 0. There's no change in the acceleration until I hit the brake. That's what the brake is for, changing the acceleration. So with this in mind, I'm going to choose one of my equations. We're looking for D, so we need an equation with D in it. We're going to use this one. D equals VIT plus AT squared over 2. Any number of them would work, but this one is convenient because acceleration is 0. So this becomes 0. 0 times anything is 0. So that whole term disappears and becomes 0, which means I could rewrite the equation as just that. It's much simpler. So when I plug in my numbers now, D equals VI is 25, time is 0.8. 25 times 0.8. What do we get? Take our trusty calculator. We get 20 meters. So there we go. In order to have enough time to put my foot from the gas to the brake, I will cover 20 meters. Now, a reminder, this is 1 meter, right? It's about the length of the screen here. Or, since we need some kind of a reference, it's about that far on me. So there we go, like this. So from my outstretched arm to my opposite shoulder. 20 of these in less than a second. And that's going at 25 meters per second. Now the problem is 25 meters per second. How fast is that? We have no real way to compare it. Most people don't know what meters per second are off the top of their head. I don't either. But we do know something. We know 100 kilometers per hour. Right? If I tell you something's going 100 kilometers per hour, you can picture that in your mind. Well, 100 kilometers per hour can be converted, and that is about equal to 28 meters per second. The conversion factor there, by the way, as we've talked about before, is 3.6. So what does that mean? She was almost going 100 kilometers an hour. So in 100 kilometers an hour, you're going to go 20 meters in the amount of time it takes for you to start hitting the brake. You haven't even started stopping yet. Started stopping, that's helpful. You haven't even begun, there we go, stopping. You've only started the process, and then you're still going to have to slow down. This is the reason why in driving, in driver's ed, they're always like, be careful about how fast you're going, because it takes time for a car to slow down. All right, let's take a look at B. We've gotten our answer for A, but what's B asking for? Here's where things get tricky. If, when the brake is applied, the car decelerates at a uniform rate of 6.3 meters per second squared, what is the total displacement of the car? Okay. So we're looking for displacement again. So what will naturally happen is that students will look at the situation, they'll look at these numbers, and they will start to assemble their picture, right? Like usual, 5 different terms. So we're going to have VI, VF, A, D, T. And at this point, students will usually start filling things in. We know that she is going to stop. Okay, well, stopping is easy. That's a VF of 0. And it tells us in the question the acceleration of the car. It says that the car is decelerating at a rate of 6.3. Now, decelerating is an English word to mean slowing down. That is a positive number. And we had said our initial velocity, which I may as well write down, was also a positive number. Now, I hope we know at this point that if I have 2 positives, I'm not going to slow down, I'm going to speed up, which means that one of these has to be negative. It doesn't really matter which one, so I'll just make that one negative. Now, the reason I'm making it negative is because it said it was decelerating. It said it was slowing down, which means the 2 of them have to be opposite. If I made this one negative, this one would be positive, opposite. Okay, so we've got ourselves some information. We know that we're doing this. Usually, though, what will happen is that students will do this. And why will they do that? Well, because it's time, and the time was told to them in the earlier part of the question. But think about it. That 0.8 seconds is how long it takes for her to take her foot from the gas and put it on the brake. Once she's put her foot on the brake, the car stopping has nothing to do with that time. Nothing at all. That time was something that happened before, not at the same time. If I were to draw a graph of this, I know, graph makes everyone immediately go, no more graphs. If I draw a graph of this, okay, here we go. Do a velocity time graph. She was traveling with a nice constant velocity. Then she hit the brake and goes down to 0. That's it. It's a very simple graph. The graphs you guys did in graph conversions and such, those are pretty complicated because it was all about learning how to do graph conversion. The problems that we're going to talk about, they're not going to be as complicated as those graphs. So, constant velocity, slowing down to a stop. That's it. That's the entire thing that's going on. But there are 2 different things there. right? The first section from here to here is 0.8 seconds. The second section could be some other time. It's not going to be 0.8 seconds. It can't be, because they're two different sections to the graph. So that is a common mistake that people will make, is they'll assume this is 0.8. It's not. You don't know what the amount of time it's going to take to stop is. And you don't know what the total displacement is going to be. But we're looking for one, not the other. All right, so how do we solve this? Well, we're going to use a different formula. Specifically, we're going to use one that has VI, VF, and A. So if we take out our list of formulas, we take a look. It's one that doesn't involve T, and because I don't have T, so the only one that's missing T is equation 4. We want an equation with D in it because we're looking to solve D, so we don't want to use equations 1 or 2. So equation 4 is our chosen equation, and it's going to be VF squared equals VI squared plus 2AD. So we start plugging in some numbers. 0 equals 25 squared plus 2 times negative 6.3, and D I don't know. Going to need our trusty calculator for this one. 25 squared is 625 minus, because there's a negative there, minus 12.6d equals 0. 0 squared is just 0. Everything, 0 is just 0. So I move the 625 over to the other side, doing a little bit of algebra. So I'm going to subtract 625 from both sides. And that's going to equal to negative 12.6d. Divide both sides by 12.6. The negatives cancel, and we're going to get a total displacement. I shouldn't say that. We're going to get a displacement of 49.6 meters going forward. Now, at this point, most students would go, awesome, there's the answer. That's not the answer. I know. Wait, what? We just did a bunch of math. You just told us there was a trick at the time, and there's still more of a trick? There is. Because it asks you what is the total displacement, the whole displacement. And the whole displacement is 49.6 for this part of the graph, but it was 20 meters for the first part of the graph. And the total displacement will be both combined. Total displacement, I'm going to squeeze it in down here. Total displacement is going to be equal to the 20 meters plus the 49.6 meters. So you're going to get 69.6 meters. And we'll round that up. It'll be a nice 70. And there is the final answer. This question is an example of one of the problems that we're going to run into, and you're going to see it many times. When you're dealing with these kind of problems, you've got to make sure you cut up the graph properly. You cut up the problem properly. This particular thing had two sections. There was the moving at a constant velocity, and there was the slowing down part. And the two of them have totally different results. And the combination of those two gives us our final answer. This is the same basic approach that you're going to get for question 8 and 9. Question 8 and 9 are going to require you to properly be able to break things down. A graph, drawing a graph, might help. But I will leave it there for now. Take another look at some of the questions and see what you can do. 8 and 9 are going to be connected to 6. 6 is very similar to what 8's going to do, but 8's going to make you go a little further. 9 is going to make you go a little further than 8. But anyway, see what you guys can do, and I will see you guys next time.